This lesson will take a look at the most important points for the climate change unit, including definitions. The first definition we have to come up with is the differentiation between climate and weather, since it is a climate change unit and not the weather change. So this cartoon kind of illustrates the difference between the two. Climate is a long-term average of temperatures and weather. Generally, climate is an average between 20 and 30 years long. So it helps you predict what the weather would be like at a particular time. Whereas weather is the day-to-day fluctuations. It's what you actually get in terms of the weather, in terms of the temperature, in terms of precipitation and things like that. So climate is a long-term average, whereas weather is short-term, day-to-day changes. So keeping that in mind, we want to take a look at what actually gives us our climates, depending where we live in the world, and then how do seasons factor into that. So the first thing that gives us our climate is our latitude, or our position north and south from the equator. And that's because the angle at which the sun's light rays hit the earth depend or make an effect on the amount of energy or heat that can actually be transferred to the land and to that area. So take a look at this diagram down below. In the summer months in the northern hemisphere, where we live in Windsor, Ontario, the sun is relatively high in the sky in the summer months, meaning that the angle at which the light rays hit the earth is more direct. So if you take a look, most of those light rays are concentrated on a particular location or point. So there's a lot of energy getting to that point. However, because the earth tilts away from the sun during our winter months, the sun gets lower in our horizon, which changes the angle that the light rays hit. So if you take a look at this diagram down here, those light rays are now on an angle and spread out. Therefore, each portion of land actually gets less light energy. Therefore, it's a little bit colder. So our latitude is what gives us our climate, our 30-year averages. Generally, it's this temperature at this given day or this month. And it's the Earth's tilt away from and towards the sun that gives us our seasons, and seasons are included within our climate averages. So the other things that give us our climate are greenhouse gases. Now, greenhouse gases are any gas that absorbs sun's radiation. So we have the sun giving off its light. A lot of it is absorbed by the earth and by the oceans, but some of it is reflected. Now that reflected energy comes back up and can be absorbed by these greenhouse gases. Carbon dioxide is the most common greenhouse gas. It has both natural and human sources. Most of the natural sources include the earth and ocean exchange, respiration of humans and all animals and plants, whereas our human sources include burning of our fossil fuels, deforestation, and things like that. Methane is the second most abundant greenhouse gas. It is mainly a human-sourced gas. There are some natural sources, but humans make most of it up, and that is mainly from our landfills, our livestock farming, and again, burning of fossil fuels. Fluorinated gases, most commonly referred to as CFCs, is the third most abundant, and they come primarily from industrial uses, so mainly a human source. They're created as a byproduct of a lot of the industries that we have. Ozone is next up, and ozone is O3, or 3 oxygens as part of a molecule, and they come because of any molecules, or a lot of molecules that contain oxygen, react with the sun and can then combine and form O3. Most of the molecules that are reacting with the sun to create ozone are from human emissions. There are natural sources, but most of them are from human emissions. And nitrous oxide is the last major greenhouse gas, and this is mainly from agriculture and farming and byproducts. There are some natural sources, but primarily human. So the main greenhouse gas produced by humans is carbon dioxide, and predominantly from the combustion of our fossil fuels. Yes, we have to take into account cellular respiration, but the predominant source is the burning of fossil fuels. So what is the greenhouse effect? The greenhouse effect isn't always bad. We need the greenhouse effect, or the earth would be like a giant ball of ice, way too cold to live on. So the sun emits sunlight and radiation, which some of it is absorbed by the earth, some of it reflected back. So the greenhouse effect is saying that some light should be absorbed by earth in order to make earth warm enough to be habitable. However, the enhanced greenhouse effect is when we build up these greenhouse gases, more and more of them in our atmosphere, we end up as the Earth absorbing more of the light's energy than we should, and therefore the Earth can actually end up getting warmer. So how does the greenhouse effect work? Is we have solar radiation, most of it absorbed by the Earth's surface, by land and by ocean, some of it reflected back. However, the more greenhouse gases we put into our atmosphere, the more radiation they can then absorb, meaning that more of the solar energy is actually staying within our Earth's atmosphere. So how is it that we actually look at and measure atmospheric conditions? Because if some documentaries and things like that, and scientists can look at this data and say, well, 400,000 BC, this is what we had. Well, we didn't have the technologies then that we do now. How is it that we measured them? If we look at this graph, we can follow the carbon dioxide concentration, and there are natural fluctuations, ups and downs, as we go through the years. Same thing with our temperature. We have natural ebbs and flows going up and down. So how is it that we measure them? There are a couple different ways. They can actually drill down into the ice, into the glaciers, and take what's called an ice core, and they can analyze the different depths of ice known to be at the surface at different years and time. They can look at fossil records, tree rings, and coral reefs. Now, if we look at the oldest record, that would be our ice cores, because they go down the deepest, they've been around the longest, whereas tree rings and coral reefs, because they are currently living things, they represent more recent years and can't show you as far back. So what are some of the effects of climate change? We'll take a look at Mount Kilimanjaro. Okay, the amount of snow on top from the 1970s to 2015 is drastically decreasing. Glaciers are melting, which changes water levels, which changes the animals that can live there. There's drought happening in many parts of the earth, meaning that what used to be a river to bring things to and from is no longer there. Crops can't be grown. There's flooding going on as well in areas that clearly didn't used to have flooding based on the way that houses were built. Okay, there are more severe storms, tsunamis, hurricanes, tornadoes. Looking at the records, they're more and more frequently occurring. And seasonal shifts. What's happening is seasons tend to change. It stays warmer a little longer into the winter, or it stays colder a little longer into the spring. Well, what happens is species that used to emerge at the same time so that the new species or the new generation of species would have something to eat. Well, now if you take a look at season shifting, those species don't emerge at the same time. So one species now coming out, let's say for example a bird, and it doesn't have anything to eat because of seasonal shift, the food that they generally depend on is no longer there. So as you can see, relatively small changes in climate are making a huge impact globally. And recall that climate is the 30-year average. So to change a 30-year average by even as little as half a degree Celsius takes a significant overall change, because that average takes a long time to establish.